5,000 meters beneath the surface of the Pacific Ocean. That's deeper than the Grand Canyon is tall. Deep enough that the pressure would crush a human body instantly. Dark enough that no natural light has reached the seafloor in millions of years. This is the Clarion-Clipperton Zone, a vast, abyssal plain stretching between Hawaii and Mexico. For decades, scientists have known it exists. They have known it is rich in minerals. They have known mining companies want access to what is down there. But in 2023, when researchers sent an AI-powered autonomous drone to map the seafloor, it found something unexpected. Not just minerals, not just deep sea life adapted to crushing pressure and eternal darkness. It found oxygen being produced in total darkness, electrical currents flowing through rocks, geometric patterns on the seafloor that appeared to be changing over time. For over a century, science has operated on one fundamental assumption: oxygen production requires photosynthesis. Plants, algae, sunlight. That is how Earth's atmosphere became breathable. That is how marine ecosystems survive. But at 5,000 meters depth, there is no sunlight. There cannot be photosynthesis. And yet, the AI drone detected oxygen being generated by rocks on the seafloor. When the research team published their preliminary findings, the response from the scientific community was not celebration. It was concern. Because those same rocks, those oxygen-producing nodules, are exactly what deep-sea mining companies plan to extract. Billions of tons of them, starting as soon as 2025. And if we do not understand what these nodules are doing, we might be about to destroy a system that is critical to deep-sea ecosystems, possibly critical to understanding how life began on Earth, maybe even critical to finding life on other worlds. This is the story of what the AI found 5,000 meters down, and why some scientists believe we are about to make a catastrophic mistake. The Clarion-Clipperton Zone covers approximately 4.5 million square kilometers of Pacific Ocean floor. To put that in perspective, that is larger than the entire European Union. It is one of the least explored regions on Earth. We have better maps of Mars than we do of the Clarion-Clipperton Zone seafloor. What we do know is that the zone is covered in polymetallic nodules. These are potato-sized rocks scattered across the abyssal plain like cobblestones. They contain high concentrations of manganese, nickel, cobalt, and copper. These metals are essential for modern technology, for example, electric vehicle batteries, renewable energy infrastructure, and electronics. Mining companies have been eyeing these nodules for decades. The technology to harvest them exists. Remotely operated vehicles can vacuum them up, process them, and bring them to the surface. It is economically viable. It is less disruptive than land-based mining. And with global demand for battery metals skyrocketing, the Clarion-Clipperton Zone represents a $1 trillion opportunity. But there has been one problem. We do not know what is down there. We do not know what ecosystems exist. We do not know what species live in the sediment. We do not know what role those nodules play beyond just sitting there being mineral rich. That is why the 2023 research mission was critical. Before mining begins, scientists wanted a comprehensive survey. They wanted to document what exists so we would know what we are destroying. They sent down an AI drone, not a traditional remotely operated vehicle tethered to a ship. An autonomous system trained on years of deep-sea footage, geological surveys, and biological data. A machine that could make decisions about where to go, what to examine, and what anomalies to investigate. The drone descended to 5,000 meters. Its mission was to map the seafloor, catalog nodule distribution, document any visible life, and collect baseline environmental data. For the first 72 hours, everything went exactly as expected. The AI drone mapped vast stretches of seafloor. It documented nodule fields, some areas densely packed, others sparsely distributed. It recorded video of deep-sea organisms, brittle stars, sea cucumbers, and octopuses adapted to crushing pressure and near-freezing temperatures. It collected sediment samples. It measured water chemistry. It documented exactly what researchers expected to find in an abyssal environment: cold, dark, mineral-rich, and sparsely populated by highly adapted life forms. Then on the fourth day, the drone stopped moving. According to the navigation logs, it had been traversing a typical nodule field when its algorithm flagged an anomaly. The drone hovered over a patch of seafloor approximately 30 meters wide. It circled. It descended closer. It activated additional sensors. When the research team reviewed the logs hours later, the drone had operated autonomously, only uploading data when it surfaced periodically. They saw something unusual. The AI had lingered over this one spot for nearly 6 hours, repeatedly scanning, taking measurements, running diagnostics on its own instruments as if checking whether they were malfunctioning. The sensor data showed why. The nodules in that patch were generating electrical current, not metaphorically, not as a side effect of some chemical process. Actual, measurable electrical voltage flowed through the rocks. Faint, only millivolts, but consistent, steady, and detectable by multiple redundant sensors. The first assumption was instrument error. Deep-sea sensors can malfunction, saltwater corrosion, pressure effects, electronic interference, but the drone had run its own diagnostics. Multiple independent sensors confirmed the readings. The electrical current was real, and it was coming from the nodules themselves. That should not be possible. Rocks do not generate electricity. Not spontaneously, not without some external energy source driving the process. But when the team analyzed the data more carefully, they found something even stranger. The electrical current was not random. It varied with the chemical composition of different nodules. The larger, manganese-rich nodules showed higher voltage. The smaller, iron-rich ones showed lower voltage. It looked like a pattern, like a system. And that is when someone on the research team asked the question that would change the entire mission. If these nodules are generating electrical current, what is that current doing? In chemistry, when you pass electrical current through water, you split the water molecules. This process is called electrolysis. The hydrogen and oxygen atoms separate. You get hydrogen gas and oxygen gas. It is a basic process. We have understood it for 2 centuries. It is how industrial facilities produce pure hydrogen and oxygen. It requires external electrical energy, usually from batteries or power grids. But what if the nodules were providing that energy? What if, under the unique conditions of the deep ocean, crushing pressure, near-freezing temperatures, and specific mineral compositions, these rocks were spontaneously generating enough electrical current to split water molecules? That would mean they were producing oxygen in total darkness, without photosynthesis, at 5,000 meters depth. The research team called it dark oxygen. If it was real, it would rewrite our understanding of marine ecosystems. For over a century, marine biology has operated on a simple model. Photosynthesis happens in the sunlit upper ocean. Phytoplankton produce oxygen. Some of that oxygen dissolves into the water. Some sinks to deeper layers through ocean circulation. Deep-sea organisms rely on that oxygen diffusing down from above. The deep ocean is essentially living off the scraps of surface productivity. That is why life gets sparser as you descend. Less oxygen, less food, less energy. But if nodules are producing oxygen locally, that changes everything. Deep-sea ecosystems might not be as oxygen-limited as we thought. Species distributions might be determined by nodule density, not just depth and pressure. Evolution in the abyss might have been shaped by localized oxygen production that we never knew existed. And if we remove the nodules, if mining operations vacuum up billions of tons of these rocks, we might be eliminating the oxygen source that deep-sea life depends on. The discovery by the AI drone raised questions faster than the research team could answer. They needed more data. They needed confirmation. They needed to understand the mechanism, so they reprogrammed the drone. Instead of mapping the entire zone, it would focus on nodule fields. It would measure electrical activity across different areas. It would correlate voltage with oxygen concentrations in the surrounding water. The drone descended again. This time, it was specifically looking for electrical anomalies. It found them everywhere. Across hundreds of square kilometers, nodules were generating measurable electrical current. Not all of them. Some areas showed no activity. But in dense nodule fields, particularly where manganese concentrations were highest, the effect was consistent. Water samples taken directly above active nodule fields showed oxygen concentrations slightly higher than surrounding areas. Not dramatically higher, this was not a geyser of oxygen, but measurably elevated, statistically significant. The correlation was undeniable. Where nodules generated electrical current, oxygen levels were higher. The mechanism was still theoretical, but the evidence was mounting that something fundamental about deep ocean chemistry had been overlooked for decades. And then the AI found something else. On the 6th day of its second deployment, the drone flagged another anomaly. This time, not electrical, structural. The seafloor in one section of the survey area showed patterns, not random scattering of nodules. Patterns, geometric arrangements. At first, the research team thought it was pareidolia, the human tendency to see patterns in random data, like seeing faces in clouds. The AI was probably just highlighting clusters that happened to look organized. But when they examined the high-resolution imaging, the patterns were undeniable. Spirals, grids, tessellated arrangements of nodules that looked almost deliberate. Some sections showed nodules aligned in parallel ridges. Others showed concentric circles. One area displayed what looked like hexagonal packing, the most efficient geometric arrangement for filling two-dimensional space. These were not small patterns. Some extended for hundreds of meters, and they appeared in multiple locations across the survey area. The research team's first instinct was a geological explanation. Currents, sediment-settling patterns, some natural process that organized nodules over millions of years. Except the patterns changed. When the drone returned to the same areas days later, the arrangements had shifted. Slightly, subtly, but measurably different from previous imaging. Rocks do not move on their own, not on abyssal plains where currents are minimal and nothing disturbs the sediment for centuries at a time. But something was reorganizing these nodules. And the AI detected another correlation. The areas with geometric patterns also showed the highest electrical activity and the most significant oxygen production. That was when the research team started using a different word to describe what they were seeing. Not phenomenon, not anomaly. System. A self-organizing system, powered by geochemical processes we do not understand, producing oxygen in an environment where it should not be possible, and potentially creating structures that serve some function we have not identified. The implications were staggering, and they extended far beyond the Clarion-Clipperton Zone. If oxygen can be produced through geochemical processes in the deep ocean, that changes our models for how life evolved on Earth. The prevailing theory is that early Earth's atmosphere became oxygen-rich because of photosynthetic cyanobacteria. That oxygen production enabled complex life. That photosynthesis was the foundation of everything. But what if there was another pathway? What if deep ocean geochemical oxygen production created oxygen-rich microenvironments long before photosynthesis evolved? What if early life did not need sunlight at all? That would explain some puzzling questions in evolutionary biology, like why some of the earliest life forms appear to have been adapted to deep, high-pressure environments. Like why certain metabolic pathways seem designed for oxygen-rich conditions that should not have existed in early Earth's atmosphere. It would mean life might have started in the deep ocean, not in shallow sunlit pools like we have always assumed. And if that is true for Earth, it could be true for other worlds. Europa, one of Jupiter's moons. Beneath its frozen surface lies an ocean estimated to be 60 miles deep. No sunlight penetrates that ice. For decades, astrobiologists have debated whether life could exist in Europa's ocean. The standard answer has been, probably not. Without photosynthesis, without oxygen, complex life cannot evolve. Maybe some chemosynthetic bacteria. Maybe simple organisms feeding on geothermal vents. But nothing sophisticated. But if geochemical oxygen production is possible, if the right mineral compositions under the right pressure and temperature conditions can split water and produce oxygen, then Europa's ocean might be habitable after all. Same for Enceladus. Same for any world with subsurface oceans and mineral-rich seafloors. The AI drone's discovery in the Clarion-Clipperton Zone did not just challenge our understanding of Earth's deep ocean, it expanded the potential for life across the entire solar system. But there is a problem, a massive, immediate, real-world problem. Deep-sea mining in the Clarion-Clipperton Zone is scheduled to begin in 2025. Multiple companies have exploration contracts. The technology is ready. The economic case is proven. The International Seabed Authority, the UN body that regulates deep ocean resources, has been developing mining regulations. Those regulations are based on the assumption that polymetallic nodules are inert mineral deposits, valuable for their metal content, but otherwise just rocks sitting on the seafloor doing nothing. If that assumption is wrong, if nodules are producing oxygen, supporting ecosystems, possibly participating in self-organizing geochemical systems we do not understand, then mining them would be catastrophic. Imagine strip mining a forest without knowing that trees produce oxygen. Imagine draining wetlands without understanding they filter water and prevent flooding. Imagine removing coral reefs without realizing they support entire marine ecosystems. That is what we are about to do in the Clarion-Clipperton Zone, on a scale measured in millions of square kilometers, extracting billions of tons of material, potentially destroying systems that took millions of years to form. And we are doing it before we understand what those systems do. The research team published their findings in a peer-reviewed marine science journal. The paper was careful. It presented the data, electrical activity, oxygen measurements, geometric patterns. It proposed mechanisms. It acknowledged uncertainties. And it concluded with a recommendation. Delay mining operations until we understand what these nodules are doing. The response from the scientific community was immediate and divided. Some researchers hailed the work as a groundbreaking discovery. They called for moratoriums on mining. They demanded further research. They argued that potentially disrupting a novel oxygen production system would be unconscionable. Others were skeptical. They questioned the oxygen measurements. Could there be other explanations? They challenged the geometric pattern analysis. Could it be observer bias? They wanted replication, verification, and wider peer review, and some were hostile. They accused the research team of environmental activism disguised as science. They suggested the findings were exaggerated to block mining. They argued that economic development should not be held hostage to speculative theories. The mining industry's response was predictable. They acknowledged the research. They praised the scientific effort. They emphasized that their operations would include environmental monitoring, that regulations required impact assessments, and that they were committed to responsible extraction. But they made clear mining would proceed as scheduled. The International Seabed Authority held emergency consultations. Environmental groups filed petitions. Several nations called for additional studies. And the AI drone descended again. The third deployment focused on answering specific questions. Is the oxygen production consistent across time? Do the geometric patterns correlate with biological activity? Can we identify the exact mechanism generating electrical current? The drone spent 6 weeks on the seafloor. It documented oxygen production at multiple sites. It confirmed that patterns changed over time. It collected nodule samples for laboratory analysis, and it found something new, something that made even skeptical researchers pause: magnetic fluctuations. The areas with geometric nodule patterns also showed subtle variations in the local magnetic field. Not dramatic, not enough to affect navigation, but measurable and synchronized with the structural changes. When nodules rearranged into new patterns, the magnetic signature shifted. That suggested the system, whatever it was, involved magnetic interactions. Possibly the electrical currents were creating magnetic fields. Possibly magnetic forces were organizing the nodules. Or possibly something else entirely, something we do not have a framework to understand yet. The research team's latest paper, published in early 2024, was more cautious than the first. It presented the magnetic data, and it acknowledged that the mechanisms remained unclear. The paper emphasized the need for continued research. But it also made a stronger statement. Whatever is happening in the Clarion-Clipperton Zone is not a simple mineral deposit. It is an active, dynamic system, and we do not know what disrupting it will do. As of mid-2024, the debate continues. Mining companies insist their operations will be carefully managed. Environmental groups demand complete moratoriums. Scientists call for more time to study the phenomenon. Meanwhile, 5,000 meters beneath the Pacific Ocean, the nodules continue producing oxygen. The patterns continue shifting. The system, whatever it is, continues operating, indifferent to human debates and unaware that its existence is now a political and economic battleground. The AI drone that discovered all of this has been decommissioned. Its mission complete, its data collected, its algorithms now being studied to understand how it identified anomalies that human researchers might have missed. But the questions it raised remain unanswered. How long has this oxygen production been happening? Millions of years? Since the nodules first formed? Or is this a recent phenomenon, triggered by changing ocean chemistry or temperature? What role does it play in deep-sea ecosystems? Are there species specifically adapted to living near oxygen-producing nodules? Have evolution and biodiversity in the abyss been shaped by this process? Could this happen elsewhere? Are there other seafloor areas where similar geochemical oxygen production occurs? Other oceans? Other worlds? And most urgently, what happens if we remove the nodules? Do deep-sea ecosystems collapse? Does oxygen production stop immediately, or does it persist in remaining nodules? Are there tipping points, thresholds where removing too many nodules crashes the entire system? We do not know. And we are about to find out through industrial-scale extraction rather than careful scientific study. The AI that discovered dark oxygen production did not editorialize. It did not advocate. It simply identified an anomaly, collected data, and flagged it for human review. But in doing so, it revealed something profound. We do not understand our own planet's ocean as well as we thought. 5,000 meters down, in the largest habitat on Earth, the abyssal plains that cover more surface area than all continents combined, there are processes we never knew existed, systems we never suspected, possibly ecosystems dependent on chemistry we are only beginning to understand, and we are about to start mining it. The technology exists to study this properly. Autonomous drones like the one that made the discovery, advanced sensors, long-term monitoring stations. We could deploy dozens of AI systems across the Clarion-Clipperton Zone. We could map every nodule field. We could document oxygen production continuously for years. We could understand the system before we disrupt it. But that would take time. It would delay mining. It would cost money that companies would rather spend on extraction. So instead, we are making a choice. We are deciding that the economic value of cobalt and nickel is worth more than understanding what those nodules are doing. We are betting that disrupting an unknown geochemical oxygen production system will not have consequences we cannot predict. And we are making that bet with incomplete information, on a planetary scale, in an environment we have barely begun to explore. 5,000 meters beneath the Pacific Ocean, rocks are producing oxygen in total darkness. Electrical currents flow through minerals that have sat undisturbed for millions of years. Patterns form and shift according to rules we do not understand. An AI drone found it. Scientists documented it. Mining companies acknowledged it. And soon, the excavators will arrive. The nodules will be vacuumed up, processed, turned into batteries and electronics and renewable energy infrastructure. And we will finally learn what those nodules were doing by watching what happens when they are gone.